going to do here is practice with our sampling distribution of means. So first thing I want to go through is just kind of an overview of what we're taking from how it's made and the center and spread of the distribution, making sure it's normally distributed so we can even calculate values. So with the sampling distribution of means, that's always going to come from numerical data. So we're going to have some numerical data that was already collected, and things that we're going to know the population data. And our population data can appear a few different ways. Our population data, it could be nice and bell-shaped, it could be skewed in some way, or it could just be really weird. It could be something like that. But with each of these distributions, we're going to have some population mean and some population standard deviation. So this information's given to us. If anything, they'll just describe the mean and standard deviation and maybe in some wording tell us whether it's normally distributed or if it's skewed or what's going on with that population data. So in our simulation, what we saw is once you have this population data, you're going through this step of taking samples, taking random samples from our population. So you're taking random samples of a certain sample size, of some size n. So you choose some sample size that we're grabbing from the population, and whenever we take those samples, that's where we saw that second window coming through in the simulation, what we'll get is a sample mean. So we're doing is seeing from one sample what's happening with that average. And we want to do this over and over and over again. We want to see if whatever our population looks like, what happens when we take infinitely many samples. And what we want to come through is a nice bell-shaped curve, where this should be the distribution of these x bar values. So everything that's under this curve, if we imagine if this was a dot plot and there were all these teeny little dots in here, each value is a sample mean from sample size n. So keeping that sample size the same, each of these values is a different sample mean that we have there. So with all of these sample means that we're collecting, we want to understand how does this distribute? Where is it centered? And how does the standard deviation behave? So what we saw is the center of it, the average of all these sample values should just be the population mean. So whatever we saw happen in the population, that's what we grab down here. And then for the standard deviation, we need to adjust it to reflect that we're taking averages of a certain sample size. So what we do is we take our old standard deviation, that population standard deviation, and divide it by the square root of our sample size. So this gives us is a distribution for our sample means. And what this allows us to do is answer questions that deal with what is the probability. So finding probabilities that the average, of sample size n is, and then go from there. But the key wording that we want to look out for here is this idea of looking for probability, or we might even be asked about cutoff values of an average value from some sample size. This average and sample size are going to go together, and it's the idea of finding probabilities with that. And when we do this, we need to check our conditions, and just to review our conditions, we need to check that we have independence. We need to check that that sample is random. And we need to check that our sample size is large enough. Again, there's kind of two scenarios here. If the population is normal, then we can use any sample size. Of course, always large sample size is best, but we can use any sample size, and it will give us this bell-shaped curve that we want. If population is not normal, then we need to make sure we have a large enough sample size. Is to have a large enough sample size that'll guarantee a bell-shaped curve. If our sample size is too small, then it's just going to mimic what's happening in the population, and we don't want to see those distributions for our means. So large enough sample size, this is where you need to make sure the sample size is larger than or equal to 30. So we'll have to know what's happening in the population to know whether or not we have a large enough sample size. So let's go through this example together. We have here a survey of students. They collected their sleep habits, and then they found the mean is 6.78 hours, standard deviation of 1.24 hours. So we're assuming they talked to all college students here since they're not describing any sort of sample size. And then what we want to note is that their sleep habits were normally distributed. So we're getting from our population data is this nice bell-shaped curve. And then mean of 6.78 hours, so that's our population mean, since this is our population data that they're describing. Standard deviation of 1.24, so that's our population standard deviation. So we have these pieces of information going. What's the probability that a single randomly chosen student gets 6.9 hours of sleep or fewer? We want to define and draw the distribution to find the probability. So we're trying to find a probability, and it's the probability for a single randomly chosen student. So if we want to know how things behave on an individual basis, that's coming from our population data itself. Like, it's not describing any sort of average here. So if we're not finding that the average is 6.9 hours, we don't want to use the sampling distribution of means. Instead, we just want to go directly to this curve, where they tell us it's normally distributed, and on average we see 6.78 for each student with a standard deviation of 1.24. So using this distribution, we want to look at this probability of getting 6.9 or fewer. So probability that x is less than or equal to 6.9. And using our technology, we should get a 0.5385 out. So that would mean there is a 53.85% chance a randomly chosen student gets 6.9 hours or fewer of sleep. So this right here, this is what we covered back when just looking at the normal distribution. Nothing new here. It's just the idea of being careful once we get into the sampling distribution of means is when do we adjust our curve. And it's because they're just talking about a single value and the behavior of a single value that we don't adjust anything. We just use the population data. But now as we go to part B, we have a simple random sample of 150 students. So what we get out of this is a sample size. They're telling us we're taking a random sample, and what we want to do right here is just talk about the conditions, which actually we don't have 4, we have 3 conditions. So let's start with independence condition. So for independence, there's 2 ways to think about it. Are the results influencing each other? Meaning, is one student's sleep habits affecting another's overall with all of this data? And that's not likely. Sleep habits should be pretty independent. However, another way to prove it is with that 10% condition, which is to say, is this sample size less than 10% of our population? Which it is. If we're talking about all college students, 150 is less than 10% of all college students, which means we can assume independence. So either of those ways prove our independence there. Next, we need randomization, which is the idea that we need a random sample. And because they tell us right there, we have a random sample, so this is met. Again, if they don't state it clearly, we're just going to assume. Only if there's wording that clearly makes it not random, then we'd avoid it, but we're going to assume randomization for most of these. And then we need to check our sample size, which our population data is normally distributed. So if our population is normal, we really don't need to check the sample size itself. It's already met. But for good measure, if our population had been skewed, 150 is larger than 30, so that would also have met the conditions there. Just if we had to say they were taking a sample of 20 students, we still would have met this condition because that population is normal. All right, defining the distribution and its parameters. So what we want is a distribution for these means, for this average sleep of 150 students. In fact, let's define our variable. So our variable is going to be for average sleep from 150 students. So we want to talk about the distribution here. We want to talk about the average of these means. So when we take all of these mean sleep from these 150 students, where should it average out? And this mean should always be equal to the population mean. So that's 6.78 they gave us. We don't need to change that. That just stays the same. Standard deviation, though, we need to calculate a little bit by taking that population standard deviation and then divide it down by the square root of our sample size. And that's going to be a 0.1012. So this variable for average sleep from 150 students, we know it's normally distributed because we passed all the conditions. If we fail one of the conditions, we can't say that it's normally distributed. It might be skewed in some way. The center of the distribution is at 6.78, and then our standard deviation is that 0.1012. So this bell-shaped curve, just to get an idea, if that's 6.78, and we go 2 standard deviations above, 2 standard deviations below, and I'm just going to round these a little bit, 6.98. We can get an idea of the number line for how the means should behave, this average sleep from 150 students. And these number lines, when we're taking averages, and same thing when we go to the proportions, it's going to be really close to where we expect to be. Especially with large sample sizes like this, we're going to squeeze in really close to where we expect to be. So to find averages far away from that 6.78 are going to be incredibly unlikely. So this distribution here is describing how average sleep habits of 150 students behave. We expect to be at that 6.78, and then this spread, the standard deviation tells us how the values spread. So for a simple random sample of 150 students, what is the probability that the average is below 6.9 hours? So this question here matches the setup for when we need a sampling distribution of means. We have a simple random sample of a certain size, so we have some sample size that we're working with. We're looking for a probability of an average. So probability of an average, you're going to need to use a sampling distribution of means. So we're going to be using this normal curve centered at 6.78, standard deviation 0.1012, and we want to look at below 6.9. So what is the probability that our variable is less than or equal to 6.9? And using our technology, that should give us a 0.8821. So going to this curve at 6.9 and then shading everything below, it's going to give us this high probability. So our interpretation there is an 88.21% chance the average amount of sleep for 150 students is below 6.9 hours. So in our wording here, we get that percentage from the probability part, and then there should be the word average coming through and a sample size coming through in your wording. So this average of a certain sample size is, and then whatever we're looking for, in our case below 6.9 hours. So that's our example for sampling distribution of means.